model-based reinforcement learning. And this is work that I've done over the last bunch of years, mostly with my students at Rutgers. We had the Rutgers Laboratory for Real-Life Reinforcement Learning, or RLQ, for about a decade. And a lot of great students came through. Yes? Not loud enough? So, no, the mic is exactly the problem. We don't have a mic. Okay. But now that I know, I think it's probably the acoustics because of the way that the back is set up. The sound must be getting lost there. Because normally I could reach somebody like you, no problem. All right. So just do that thing you just did if I get soft again. But otherwise, I will project and I will fill this room. All right. So the plan for the talk is to give a little bit of background in terms of reinforcement learning, and specifically model-based reinforcement learning, what some of the issues are when you try to put planning and learning together to do decision making. And then I'm going to move from there to how do you handle larger state spaces on the learning side and also on the planning side, and what sort of algorithms seem to be able to accommodate this combination of problems. So just to kind of set things up, this is maybe not a very useful problem, but this is an example problem of a real-life reinforcement learning system. This is an IVO robot, back when they used to exist, that's trying to turn around to face the pink ball. And what it's doing is it's actually taking actions in the world, observing the effects of those actions, and observing whether or not it's actually achieved its objective, which in this case is seeing the pink ball. So this has all the elements of a reinforcement learning problem. It's deciding which way to turn to try to minimize the amount of time or steps. So then, all right, now I have to remember not to yell. All right, so the robot is trying to figure out which way to turn, that's its action, to try to minimize time, that's its objective, to see the goal, or the ball in this case, and it's using camera input as a representation of its state. So you probably know all this already, so I won't belabor it any further. The model-based approach to these kinds of problems is basically to break this into two pieces. Learning about the dynamics of the world, learning about how the actions or the decisions that the agent can take actually impact the world, and then planning, deciding, okay, if that's how the world works and this is what I'm trying to do, what should I do? What action should I take now? That actually causes changes in the environment. So the robot maybe turns a little bit. And that information, that experience actually can go back and also feed into model learning again, so that the system could actually be getting more and more information about how the world works so it can plan more effectively. So this is all well and good, and in some sense, we have a community, like the machine learning community, that studies the learning piece, and we have the ICAPS community studying the planning piece, so, problem solved. The thing that makes this hard, I think, mainly, is that you can actually think, or the system can actually think something is bad that's actually quite good. And because if it thinks it's bad, it won't plan to actually participate in that part of the state space, and therefore won't learn that it actually is good. And there's a lot of examples of this. This is a kind of standard chain world example, but when I was working on the slides, it occurred to me that I had an issue like this with one of my nieces, who decided the first time that she met me that I was evil incarnate, and that the more that I tried to interact with her to try to get her to realize that I'm good, the more she thought to herself, that's exactly what an evil person would do. And so she had decided that I was really bad and just wouldn't engage with me. Seriously, wouldn't engage with me at all. It was just horrified of me. And so I think she missed out on some very positive rewards, because I'm actually a lot of fun to play with. So that's an example. All right. So a solution to this problem that is really common in the community is the notion of optimism in the face of uncertainty. So this is basically the idea that if you don't know, assume it's good. So in this chain example, you don't know what's at the end of the chain. If you assume it's some big reward, then, well, two things could happen, right? You could go and it turns out it's a great reward, it's big, we're happy, I'm glad we tried that out. Or it could be crappy, and then you get out there and you're like, okay, now at least I know it's crappy. So I know that I'm not missing out on anything exciting. So this notion of optimism in reinforcement learning goes way, way back. And in fact, you can think about A* as being another example of this kind of idea. Just, if you haven't checked it out yet, assume that it's good. But in the reinforcement learning community, there's kind of 3 threads that have come together to really kind of push this idea forward. Back in '93, Moore and Atkinson talked about prioritized sweeping. What they did in their algorithm was, if a transition is underexplored, then assume that it has high reward, which kind of rhymes. So I worked that into a video at some point. So the idea being that you're going around in the environment, and if there's a transition that you haven't tried enough to have an accurate estimate of it, then assume that it's really good. And again, it will have this effect that it will draw the agent to explore that part of the environment and either discover it really is good or discover that it's bad, but it knows that it's bad and it can move on to other things. So this is a great algorithm. It was very effective. A number of years later, Kearns and Singh came and said, well, you know what? We can actually make this more precise. If we distinguish between known and unknown transitions, like I know what happens. I have an accurate model based on my experience of what happens if I take this action in this state. And I can partition all of the transitions in the entire state space as the ones that I know about and the ones that I don't know about. And what they showed is that by making that partition, they can actually get polynomial time guarantees on how much experience the agent's going to need before it starts to behave near optimally. So this was a really cool way of thinking about the problem. People just their heads weren't there before this. It was about coming up with learning algorithms that in the limit converged to optimality. This was like, no. We can actually, in polynomial time, get something that's close to optimal. And Ronan and Moshe came up with the idea of, well, wait a second. Actually, pretty much this algorithm can be analyzed using these ideas, and what we get is something that is simple and provably effective. So the idea of Rmax is that what we're going to do is we're going to have, well, I think I have a slide. Yes, all right, so here's the idea of Rmax. So what we're going to do is we're going to learn a model of the environment, and the model has 2 components. What's the reward that I'm going to get if I'm in some state and take some action? And what's the transition probability? If I'm in some state and I take some action, what's the probability I'll go to some other state? So those are the things that I need to estimate. What I'm going to do is I'm going to choose some value c in advance, some integer, call it 15. And what we're going to do is as we're moving around in the environment and exploring and taking actions, after we've seen some state action pair c times, 15 times, meaning that we were in that state and we chose that action, then what we're going to do is we're going to nail down an estimate. We're going to say that the expected reward is the average over all the times that I've tried that action in that state. And I'm also going to come up with an expected transition probability. So the probability of reaching some state is, well, how many times did that happen divided by the number of times that I tried it. So these become empirical estimates based on the C samples. But before that point, before that C is reached, we're going to assume the following: that the reward that we get for choosing that action in that state is Rmax, is the maximum possible reward in the environment. And the transition probability, what's going to happen is if I choose that action in that state, I'm going to go back to that state and more awesomeness will happen. All right? So, like this is a state in the world that I don't know about it, but what I think is going to happen is it's just going to be nirvana. I'm just going to get there and like I could just chill out there as long as I want. I could just stay there and get maximum reward. Of course, what happens is eventually you do that a bunch of times and you're like, oh, I hit 15, I put in the actual estimate, like, oh, this wasn't as good as I thought, and it moves on. So it builds this artificial model, an estimate based on its experience, or if it doesn't have enough experience, something very, very positive, and then it selects actions optimally for that model. So it plans in that not really accurate but useful model of the world. All right, so any questions about that? Is that clear, the structure of this? I have a tendency to belabor it if I think that people don't get it, but I think it's a relatively straightforward idea. Okay? All right. So there's a couple cool things that we know about this algorithm. So this parameter C controls the amount of exploration that the algorithm is going to undergo. So if C is set very high, so 50, I need to see something 50 times before I really believe what I've seen. And so it tends to explore longer. It goes out in the environment and caresses all the walls and checks everything, every possible thing. It wants to see it lots of times before it's really convinced it knows what's going on. If you set this value C much lower, like 2, it explores a lot less. It sees something, it thinks it understands it, it moves on. The problem, of course, of setting it too high is that you're spending all your time caressing the environment and not actually getting high reward. The problem with setting it too low is you can be wrong, right? You can actually think that a transition is very unlikely, that actually is reasonably likely and very high reward, and it might end up dismissing it, right? It might end up, this self-reinforcing pessimism might happen. But what we know from Brafman and Tenenholtz is that we can set C so that things are good. And good is going to be defined as follows. So you give me an epsilon and a delta in an environment that has k actions and n states and has some discount factor gamma. We're going to define a mistake. The agent's going to be moving around in the world, going from state to state. We're going to say a mistake is any action choice that it makes that is more than epsilon suboptimal. Right? It's worse than epsilon from what you'd be able to get if you took the best action. What we know is that the total number of mistakes that this algorithm Rmax will make, if assuming C is set correctly, is on the order of the square of the number of states times the number of actions, divided by 1 minus gamma cubed and epsilon cubed. And so this bound holds with probability 1 minus delta. So it's a polynomial. It's not a great polynomial, but it's a good place to start. So we've got an algorithm that has these nice guarantees. It's going to move around in the environment. It's going to explore what it needs to explore, and it's ultimately going to be gathering near maximum reward at all steps but a few. And it has to plan, but it doesn't have to plan that much, right? At most, it's going to discover the cth time that it visits a particular state action pair. It'll do a replanning. But that can't happen more than the number of states times the number of actions times the C parameter times. So, good. Now, of course, the problem with this, if you're a planning person, if you're a reinforcement learning person, you may not have a problem with this at all. But if you're a planning person, you're thinking, scaling with the number of states. Now, I can very easily write down a model that has an awful lot of states. That's not a good thing, right? You're going to take a very, very, very long time to solve these problems if the number of states is large. So we have to come up with some way to scale up. And both of these components need a little bit of attention for this to work. We need to figure out how to use our experience to learn a model where we don't have to see a transition, every single transition, C times to believe them, right? We need to somehow learn about some transitions while we're actually taking other transitions. We have to generalize that information from one place in the state space to another. That's not so horrifying. Maybe there's good ways to do that. And we also have to worry about the complexity of planning. If the MDP that we construct is very, very large, again, we can't have the computational time to do that grow with the number of states or the number of states squared. We need to somehow be able to make a decision that we're pretty confident in without computing a full policy of deciding what to do in every possible state, all possible contingencies. And again, that doesn't seem so scary. This is what we do in planning all the time. So there's at least the hope that we can somehow plug these two things together and be able to learn and plan in very, very large environments. So I'm going to focus on these two pieces, one after the other. First, I'm going to focus on the learning piece. This is kind of what we did the most on. And it kind of sets the stage for constraints that the planner is going to have to deal with later. So here's what we need. Here's a way to think about this. So what we would like is to learn the transition model. The transition model tells us if I'm in some state and I take some action, what's going to happen? What's a probability distribution over the states that I'm going to reach next? We have to generalize. We have to come up with a way of learning this mapping in a way that we don't have to explicitly memorize every single possible combination of state and action. So we need to generalize, but we need to generalize safely somehow. And what exactly does that mean? So the way that we ended up formalizing this is a concept that we call KWIK learning. KWIK stands for knows what it knows. So this is an algorithm that is going to be able to make predictions, accurate predictions based on its experience. But at the same time, it knows when it doesn't have the ability to accurately predict a particular transition. It can separate the known from the unknown, just like we need for these reinforcement learning algorithms. So the setup of this is yeah, when I get close to that speaker, bad things happen. All right, I'm going to stay over here. I like moving more, but I'm afraid of the speaker. All right, so here's how the knows what it knows setting works. We imagine that there's some hypothesis class H. So we know the identity of this hypothesis class. however transitions work, they're somehow taken from that class of possible transition functions. And we don't know what the transition function is. We don't know some function f. It's hidden from us. But we know it's a part of that class. Now what's going to happen is somehow the environment is going to present us with inputs. And what we have to produce as a learner, given the input x, is f of x, the actual output that the function that we don't know would produce given that input. Now, of course, that's really hard to do, especially if we haven't really if we just started learning. So we're also allowed to punt by saying, I don't know. Right? So this is you have two options. Either give me the right answer or say you don't know. Now, that, so far, is actually a really easy problem to solve. To come up with a learner that either gives the right answer or says, I don't know, it's like, while one, say, I don't know. So the extra constraint that we need to put on this to make it work is that you can't say, I don't know too much. Right? We need a bound on the number of times that the algorithm will throw up its hands, and that bound should somehow be related to the complexity of the learning problem itself. So those are the constraints now. We want an algorithm that's going to, if it can't make an accurate prediction, say I don't know, but each time it does that, it better learn something because there's going to be a bound on the number of times it's allowed to say I don't know. All right. So if we could solve this, and I haven't said how we would do this yet, but if we could solve this, it's very well suited to model-based reinforcement learning. And the reason for that is that, first of all, it doesn't make any assumptions about the distribution of the inputs, which a lot of learning, like the PAC learning framework, is tied to the input distribution. The assumption is, I have some training examples, they come from a distribution, my testing examples will be drawn from that same distribution. If that's violated, we don't know what the learning algorithm is going to do. But this setting there is no dependence on that distribution. These inputs could be selected adversarially, perhaps. That's a good thing. Why is that a good thing? Because if you're learning about an environment by actually exploring that environment, the distribution with which you're going to get different inputs is going to change over time because your behavior changes over time because that's what learning is trying to do, right? Like it would be horrible if that was not the case. It would be, I'm allowed to learn about my environment, but I can't ever use anything that I learned because that would throw off my learning algorithm. So this is a useful thing to be able to say, is that it's distribution independent. And in addition, by being able to distinguish between known and unknown states, we can use that to drive exploration, right? We can say, there's transitions out there that we don't know about yet. Let's assume they're really good to make sure that we learn about them. And once we get out there and learn about them, we're not going to be confused about what we're learning for very long because there's a bound on the number of times that we won't know the answer. All right, so this is a really useful thing. It's not entirely clear a priori that we could come up with learners that have these properties, but these would be good properties to have. So let me give a really simple example that actually is at the core of most of these algorithms anyway, so it's not a completely irrelevant example, where we can actually do this quick learning. So imagine that we've got a coin, and what we're trying to do is predict the probability that it comes up heads. Given m coin tosses, we might predict, m coin tosses and s of them came up heads, we would estimate the probability as the number of heads divided by the number of flips. Okay, so that's not so surprising. What's nice is that the Hufting bound actually gives us a way of relating that estimate to the actual probability of coming up heads. And what it says is that if we take the empirical estimate for a variable that can take values in this range, based on m samples being more than epsilon away from the true value, the probability of being off is bounded by this nice exponential expression. And what we can do then is invert this and say, okay, we can solve for m. What does m need to be? How many times do we have to flip the coin so that we're reasonably sure that we're reasonably close to the right answer? All right, so given that we have this kind of bound actually for decades and decades, this gives us the ability to quick learn transition probability. So what we do is we say, I don't know, until we've seen enough transitions, m transitions, that's big enough so that the probability that we get out of this is close to the real answer with high probability. Okay? And that's essentially, right, if you think about it, that's essentially what the Rmax algorithm is doing. It's kind of putting off making a commitment to its guess about the probability until it has gotten enough data to accurately estimate those probabilities. All right, so that's one thing we can quick learn. We have a paper where we just throw out as many things that we could think of that are quick learnable. A lot of them build on that idea, but there's other kind of cool combinations that you can do as well. Probably the neatest one is that you can quick learn a noisy linear function. So the algorithm ends up depending not on the the size of the input space, which is continuous, it's infinitely large, but instead on the dimensionality of the space. So if it's a linear mapping, we can actually learn with a bound that is polynomial in the dimension of the linear space that we're learning in. So that's cool, and that ends up being really helpful for learning probabilistic strips type rules, right? It's useful to be able to figure out, based on observing an outcome, what the probabilities were that actually generated that outcome. What's the linear probabilistic function that actually generated the observed discrete outcome? So we have a whole bunch of these algorithms that we've shown are quick learnable, and these can form the building blocks of reinforcement learning algorithms, right? As long as our transition function that we're trying to learn can be made out of these various kinds of quick learning classes, or quick learnable classes, then we've got an algorithm that can actually get some guarantees behind it. I've just started to play with this idea on this slide very recently, but I really like it. But I'll admit a priori that this is a fiction, right? So don't believe what I'm saying next. But I think it's a really good idea. Just don't. Okay. So there's a couple attempts have been made. I don't know if you guys know about the Church programming system or Figaro. A bunch of people are thinking about probabilistic programming. What they mean by that is expressing as a high-level program a generative process, a probabilistic process, so that we can actually reason about it through the program itself. So using the program not as something that we're going to run, but as a specification for where probabilities are coming from. And so this has been done really, really elegantly, I think, in the context of Bayesian reasoning, where you could say, here's how outcomes are produced, here's the actually observations that we've made, now run the program backwards, essentially, to figure out what the hidden parameters must have been that produced the outputs that we saw. It's a neat idea. And what's cool, I think, one of the things that's cool about KWIK is that there's so many different pieces, there's so many different ways that these ideas can be combined that would also work as a kind of a programming language. So this is how I would express the coin flip example as a program that could then be reasoned with to generate an actual learning algorithm. So the program is expressed as a forward process, the learning is then going to invert that. But the user, as it were, doesn't have to care. So what we say is that P is some hidden parameter. It's the probability that our coin comes up heads. It's something between 0 and 1. The world selected it. We don't know how that happened. So that's what this first line is saying. So P is some parameter basically between 0 and 1. We don't know what it is. Then we tell it, OK, we flipped a coin with that probability, and we observed that it came up heads. Then we flipped a coin with that probability, and we observed it came up tails, and heads, and heads. All right. At the end of that, we can then ask, can you predict what this value of P is to within a precision of 0.1, and your prediction should be accurate with 25% probability? Or, sorry, should be wrong with no more than 25% probability. And so what this would do in a quick setting, it would either return, I don't know, because it doesn't have enough data yet. Actually, in this case, it wouldn't have enough data yet. This is not enough flips to really nail down the probability. Or it would actually give back the value. It would give back a number that would be close to the actual answer with high probability. So I find this kind of a useful way to think about it, because we can actually, again, as a forward generative process, we can specify what is it that we're trying to learn, and then let the system actually figure out how to build a learning algorithm out of those ideas. So let me just to finish that thought, here's how I would write in the same kind of language that doesn't exist. Rmax. So this is, you should be impressed that this is cool. We can make Rmax on one slide using a programming language that doesn't exist. It does make it a little easier, I think, to make it all fit on one slide. And then I'll assert that there's an Rmax primitive. All right, anyway, so here's Rmax expressed as a learning program. So the basic idea is that we say, well, we have to say what the model is. What is it that we're trying to learn? It consists of a bunch of transition probabilities from state in action to next state. And what that is actually a partition. It's a set of numbers that sum up to 1 of size the number of states in the state space. So we don't know what it is, but we know it's like a multinomial distribution, right? It's a bunch of numbers that add up to 1. Again, we don't know what it is yet. The reward function we know it maps to some value that's between negative Rmax and Rmax. So it sits in some range. I guess R min to Rmax would have been a better way to say that. And then what happens is now we get some data. So what does the data tell us? The data says that if we observe a transition from state action to a next state with some reward, or a SARS, as we call them, in the set of trajectories that we've actually experienced, what we're really saying is that this S prime was chosen from a multinomial distribution with these parameters, which we don't know, but we know, what we said that they exist. And that's where it came from. That's where this S prime came from. It was an observation drawn from this multinomial. And then, I don't know, I just made this up, this idea that maybe the reward is some random number between its expected value minus some spread plus some spread. So the rewards are random, but they have as an expected value whatever this R value is. And we observe what that is. And if we observe enough of these, then we should start to be able to make accurate predictions. And in fact, so here's the Rmax part. It says, let's go through all state action pairs and try to make a prediction as to what the probabilities are. If we don't know for a given state what the transition probabilities are or what the rewards are, then we're going to build a transition function that is just a self loop back to itself with maximum reward. But if we can make these things, make both of these predictions accurately, then we build a model that actually uses that prediction of the transition and reward. And now that we've built that MDP, we solve it and act according to it. All right, so that's, in a nutshell, that's how this should work. This would be a very nice way to be able to specify these kinds of learning algorithms, because it just goes straight to it. This is the thing that's missing. This is the thing I'm trying to learn. Here's how they relate to each other. I don't want to worry about the details. It should just work out. All right. So one thing we did, so we haven't built that. But thanks for letting me tell you about it. What we did do, though, is we have a general, at least on paper, we have a general format where we can take any quick learner and connect it up in this Rmax setting. And the form of it is we use the quick learner to learn the transitions. We build an optimistic model by saying for each state action pair, do we know what it is? If so, fill it in. If we don't know what it is, assume it's awesome. Then we've put that through a planner, which in this case is usually value iteration for us. So you build the entire state space and you do dynamic programming to find the value function, act according to that, feed the experience back into the learner. What we know about this combination of quick learning and at least an epsilon accurate planner is that we can learn behavior that is probably approximately correct in an MDP. That is to say that it only takes a polynomial number of suboptimal steps over its entire lifetime with high probability. So that's cool to be able to have these two pieces. Again, the quick learning piece, if we give it some information about the structure of how the transition probabilities work, great. And then we need some way of doing the planning. All right. So let me just show you that kind of works. We did it not just in these flat MDPs where every state action pairs are separate, but in various ways of actually being able to generalize between transition probabilities. So here's a classic example is the taxi problem. Where are we on time? Do you know? Okay, all right. So yeah, I think I don't want to say too much more about this, but the basic idea here is that let's say we know a priori. No, maybe I should say a little bit more. So this is the taxi problem. So in the taxi problem, we live in a grid. We're a taxi. We can go north, south, east, west, move around the grid. There are some special places in the grid that are marked with colors. This is sort of colorblind, I guess. Red, yellow, blue, green. And yeah. So and at each of those positions, a passenger could appear, and the passenger has some destination that it wants to go to from among those different possible destinations, the four. So the number of possible states in this environment is about 500. So there's 25 different places the taxi can be, times 2 different places, whether we're holding the passenger or not, times 4 the number of different places the passenger might want to go, times 5 the number of places the passenger might actually be. So multiply it all out and you get 500. You can learn this with standard reinforcement learning techniques, but you can also learn it even faster by doing this sort of quick Rmax idea where what you do is you say, okay, I know something about the way that transitions work. I know that when I am moving, it doesn't change where the passenger wants to go. I don't know how moving works, but I know that these two things are statistically independent of each other. So I can express all that information, maybe that I know a priori, as a kind of dynamic Bayes-net model, right? That says this is for what? The pickup action. So picking up a passenger has the property that the new taxi location depends on the old taxi location. The new destination for the passenger depends on the old destination for the passenger. And where the passenger is after pickup happens depends on two things, both where it was and where the taxi is, right? So if the taxi and the passenger are in the same place, pickup puts the passenger in the taxi, maybe with some probability. Otherwise, you can try to pick up a passenger who's far away, but it doesn't work because they're too far away. So we don't know exactly what the numbers are. We don't exactly know how things relate to each other, but we know that there's some independence here. So if this graph structure is known, learning the transition probabilities is a quick learnable problem in the size of those structures, right? It doesn't depend on the state space directly. It depends on the interaction between the variables. So that's really great. And in fact, if you run this in the taxi problem, it very quickly picks up how things work, right? It learns how the movement works. Separate from it learns how picking up works. Separate from it learns how putting down works. It learns very, very quickly. And we can even do this sort of thing in continuous domains. Let me just show you it. And I'll try to explain it. If it doesn't make sense, it doesn't make sense. All right, so that's not a robot. That's a robot, sorry. So this is another IBO. It's being tracked from above, which is why it has that lovely little fanny pack thing going on. And this is a bumble ball. It's actually just a little mechanical toy that you can get from a store that just wibble wobbles. And the agent's goal in this case is to try to get to the goal location, which is the bottom right corner. So the robot's trying to get here. It gets high reward if it gets here. But it's trying not to touch the bumble ball. So the size of the state space is actually quite large because the position orientation of the ball and the robot both matter. And it very quickly is able to learn how transitions work and then plan in this environment. And you can see that it's not a completely trivial problem in the sense that even though this is just a random influence, sometimes it just seems devious. It's like, really, bumbleball? Really? So the agent is trying to come up with some way of getting to the goal, but it really doesn't want to bump into the bumbleball, and it's giving it a nice wide berth. The video. Another thing I like about this video is that what's that? It never ends. No, it'll get there. It'll get there. Is that it's almost there? It's almost there. Success. All right. Is that I don't know if you noticed, but the robot was walking what we would call backwards. But it doesn't have eyes. In this case, the eyes are above. It's seeing itself from above, and it's just trying to maximize or minimize the time it takes to get to the goal. It just turned out that the walking behavior was a little bit more efficient in this direction. And so that's one of the things I like about these reinforcement learning things when they surprise you. It's like, oh yeah, I know better than you do how my body works, so I'm going to minimize time the way that it works. All right, but anyway, in this particular case, what's happening is it's learned. We gave it a model that said, well, there's three variables that are relevant here. Where's the ball? Where's the robot? And what's the angle of the robot? And we don't know exactly how these things work, but we think we're going to assert that the change, for example, in the robot position depends only on the angle that it's facing, right? So we give it a bunch of these dependencies. It's a lot less to learn, and it can learn it very efficiently. We did some stuff with Pitfall because, 80s. All right, so here's the thing, though, about all these algorithms that, well, I'll play this video and I'll talk over it. This is another example, and what we did in this particular case is we told it that the way that dynamics work in this video game, again, the different actions depend on what's touching what, essentially. If this player is touching a ladder type object, then it's going to behave some way. I don't know how, but it's going to depend on that. But it doesn't depend on things that it's not touching that are very far away. And what ends up happening is when you run like a quick Rmax algorithm on this environment, it has a very, I would say very human-like exploration that it tends to engage in. It goes and checks things out, and then it moves on to the next thing, right? It doesn't try every action in every state, which looks really ridiculous. It checks out how pits work, how ladders work, how walls work. In this case now it's checking out how logs work. And then once it knows that, it can actually plan a route directly to the goal without getting distracted by all the different things that happen. And all we told it in this case is that transitions depend on which objects are in contact with which other objects. But other than that, it had to figure it out. That's a little happy dance at the end. So this is really cool, and the way that this worked is it ran one of these learning algorithms to figure out how all the objects interacted. Then what did it do? It planned, and how did it plan? It wrote down all possible states that are reachable according to the operators that it knew, and then it ran value iteration. So this is embarrassing when you get right down to it. So you can take a little problem like taxi that it's very small to look at what the state space looks like. It's very tight to say what all the actions do. But then when you go to do the planning, it's like, well, we multiply out the number of locations times where the passenger is, times this, times that, times this other thing, times this other thing. And then you've got 500 states. And now, okay, good, now I'll start the planning. Well, you've already wasted your life, right, just creating the state space and planning in it. We need to plan directly somehow in the learned knowledge and not in some expansion of it. So that's what I would like to focus on for the rest of the talk. What do we have to tell the planner so that it can use this kind of information that the learning algorithm is determining? We need something that doesn't blow up with the size of the state space. We need something that can extract the model from the quick learner, right? Because the quick learner's job is to figure out how transitions work, but it's done in this query fashion. I ask you, how does this transition work? And the system says, this one works like this. How does this one work? I don't know about that one. You'll have to assume something optimistic. So it doesn't have a nice tight representation of the entire state space and all the uncertainty. It's not like it spits out something in PPDDL or something like that, right? It actually it's just sitting around waiting to be asked, what does any particular transition do? So we need a planner that actually is going to have that kind of interface, use that kind of knowledge to decide what to do next. It would be nice if the planner actually had epsilon delta bounds so that the overall system would have some nice guarantees. But, you know, it would be nice. All right, so what we started to realize is that algorithms that use sampling and use this forward model in various ways fit nicely with this. And these are the kinds of algorithms that we ended up focusing on. So tree search is a good one. So what does tree search say? Tree search says at any given moment in time, I'm at some state, and I'm going to look forward from that state and say, what are the different actions I can take? What are the different outcomes of that action? If I look far enough into the future, I can make an action now that is guaranteed to be close to optimal. So that's a great idea in that it's a terrible idea. No, it's a great idea in many ways, but it's a bad idea because if we have to consider all the actions that we can take, and for each of those, all the states that could happen next, that could be our blow up right there. In fact, it could be much, much worse than actually planning, using some kind of dynamic programming algorithm on the full state space. So that's a bummer. But Kearns, Mansour, and Ng said, well, you don't actually have to look at all possible next states. In fact, there's some value, C comes up again, that if we actually take, consider all actions, and from that, just a sample of possible next states, which is easy to generate because we actually have a concrete state at each step along the way as we build this path. That there's a non-size of the state space dependent branching factor that we can put in here so that if we actually solve this tree out to some depth, that we get a near optimal action at the root. So this is great. This actually fits together really, really well with the overall KWIK idea. The problem with it is that it's completely impractical, just completely impractical. So if we have the size of what that branching factor needs to be, if the number of actions is, say, 2, which would be small, you can't get any smaller than that and still call it planning, and we have a pretty substantial error tolerance of like 0.1, pretty reasonable discount factor, not a very wide rewards, the size of the tree that you actually have to build to get guarantees, is only 10 to the 12th, which is polynomial in something, but that's a really big number. We can't I said to my students once, just implement this and get back to me, and they came back to me like, no, we can implement this, but you're never ever going to be able to run anything. So yeah, even though the bounds look really nice in the paper and they're all pretty and stuff, the actual numbers end up being enormous. So we need an approach, at least with better best case performance, right? If the planning problem is well behaved, you shouldn't have to build a tree of this size. So what we ended up doing is building on ideas from Monte Carlo tree search, the idea of basically pruning this tree. trying to get a good answer, but instead of doing it, systematically build out the entire tree and then percolate the values back, we're going to kind of zoom down from the root a number of times. So the basic structure of this, here's a concrete example. I think I actually took this example from Wikipedia and then made it my own. So we've got some kind of a tree where, again, the maxes here are because we get to choose actions. The expectation is because we've taken some sample of next states. What we can do is kind of dive down. Say, from my current position, maybe I'll take this action, and maybe this outcome will happen, and maybe I'll take this action, and maybe this outcome will happen, and I'll get 5, which I haven't learned a lot yet, but I learned something. I can then propagate that information back up to get ranges that say, okay, well, the actual expectation here isn't going to be 5. It's somewhere between 3 and 7.5. The maximum here is going to be somewhere between 3 and 10. The expectation here is somewhere between 2 and 10, and so forth. I can propagate these bounds back up. And then I can use those bounds to decide how to dive down again the next time. In particular, at a max node, I'm always going to dive down to whichever one has the highest upper bound. This is that optimism idea coming out again. And if there's a tie there, then whichever one has the widest range. And at these other nodes, at the chance nodes, I will go to whichever side has the largest range of possible values. And I can do this a number of times. And what I can show is that after I do this, at some point it will stop, which is good. The maximum amount of time it'll take before it stops is the size of the tree, which would be bad if that happened, but at least it's not running forever. And in fact, it can actually prune a tremendous amount off from what the full tree would require. So each traversal closes a leaf, gives us information about the value of that leaf, and the bound information is propagated back up so that we get a nice, focused sense of what the values actually ought to be. All right, we've run this on a bunch of problems, planning-ish kinds of problems, like a paint polish domain, and it behaves better certainly than value iteration, right? So value iteration actually has to build out the whole state space. Of course, that runs into trouble when the state space gets big. It also crushes sparse sampling, where you have to build that full tree, because that tree gets really big really fast. And it also does better than some other top-down algorithms like UCT, which don't have these nice guarantees about how the bounds work. All right, we did that on a couple different domains. I want to show you just one other kind of example of how we've been doing planning in these learned models that I think is really neat. The videos are fun, so that's why I want to show them. So another way to look at the planning problem. All right, so the agent has interacted with the world, and it builds up a model of how transitions work. And now it has to decide what to do. So one way to do this is to say, okay, I have a model of how transitions work. That gives me essentially a simulator. So I can run experiments in my head, not in the world. I'll do them in my head. Something interesting will happen, and then I'll use that to actually act in the real world. And so what is this problem? The problem is I need to use my simulator to find a policy, to find some way of acting that has maximum reward. So this is essentially an optimization problem. Find me a structure, find me a plan, so that if I run it, it has maximum possible reward when I run it in my simulator. It's a hard optimization problem because it's very noisy, right? So even my simulator it has probabilities and stuff in it. So it's the case that when I run that plan in my mind, it can have different outcomes at different times. But that's okay. There's algorithms that can deal with that. So let's use them. So we're going to propose a plan. We're going to use our quick learned model to compute its value through simulation, mental simulation. And then we're going to just keep repeating until we find a plan that we think is good enough, and we'll use that to act, at least for a little while, at least till we've learned a little bit more. Maybe we need to replan again after that. So one of the ways that we've gone after this is by actually applying a kind of off-the-shelf optimizer, cross-entropy optimization, which is pretty robust to noisy samples. And what's happening in this point is this video here is there's a this is like a stick figure-y kind of thing. It's trying to walk across the screen, but there's force happening to it. There was each of its joints experienced some kind of backwards force at each step along the way, and it was trying to somehow kind of fight through the random snowballs that it was being hit with to make it across the screen. And the planner itself was just this generic optimizer. It just was running simulations and then finding what seemed to work well and then trying it in the world. We thought that worked really well, so we decided to try a slightly harder problem of getting it to walk down some steps. So this is what happens when we applied the same algorithm to planning in this setting. So that was surprising. It worked. It was pretty good. I mean, after that, we're like, we have to make this different. We have to make more steps or make it taller or something like that. But anyway, we decided to just stick with this because, again, it's fun when these things sort of surprise you. But anyway, so what's happening here is it's just applying this cross-entropy idea. There's some better optimizers that have come up in the last few years, and we've been starting to gear up to use those as well. But it's an interesting way of thinking about this problem. It's one way of handling the noise. Here's another one, which is to view decision-making as a kind of a bandit problem. Bandit algorithms, bandit optimization problems are pretty good at dealing with this fact that the same outcome or the same action can have different outcomes at different times. So we decided to apply this in the setting of this sort of Mario world, where it's just trying to get to the right side of the screen. It's really good. I wouldn't want to be that. So again, what's happening here is that it's actually generating sequences of actions that it thinks might work out, and then trying them in its simulator to see whether or not they did work out. And if they didn't, it very rapidly just throws it away and tries another one. So what's cool about this particular environment is that it's actually not that hard to find a good plan for it if you don't try too hard. Just try a whole bunch of random things. One of them is likely to work. Like 1 in 1,000 of these plans actually worked. So you just have to be able to spin through them fast enough until you hit one that works. It's not using any kind of local search information, which we're not sure would be very informative in this kind of task anyway. It's like this is a reward-rich environment. It's the kind of environment where lots of things are likely to work, so we just have to try enough of them, being robust to the noisiness of the outcomes. All right, so that was the examples that I wanted to show you. The overall message is that model-based reinforcement learning is just learning and planning together, but there's a twist, which is that they need to have this optimism kind of at the border between them. So the learning has to be able to produce optimistic estimates, and the planning has to be able to deal with those optimistic estimates. And the way we did that on the learning side was with quick learning, and the way that we've been trying that on the planning side is to use more sample-based methods, tree search, and noisy optimization. So thanks very much for your attention.
So great talk, Michael.
Thanks.
So optimism is great if you're trying to be optimal in the end. Mm. And you started with this example of your niece who interacted with you and then wasn't sufficiently optimistic. But if she were to be optimistic, she would end up having to interact with you once and then say, oh, wait, maybe my favorite person is somebody else. And then maybe my favorite person is somebody else. And she'd have to interact with the billions of people in the world before she would come back to you. Mm. And it's in many cases, you know, our agents, especially if they're robots, don't have time to try everything. So I guess the question is, like, you know, what is there some limit to sort of enforcing? I mean, I agree what you're doing is necessary if you're trying to be optimal. What do you do if you're going to give up on that optimality and just try to be good?
Right. Good. So, great. So one answer is satisficing, right? Is to say, okay, well, it's good enough. If you have some kind of aspirational level. The way, though, that I've been thinking about it more recently is if the agents really are autonomous, they're dropped into the world and now they have to somehow become optimal on their own, you're kind of stuck with something like this. Either be happy with being suboptimal or be willing to meet all the billion people to see who's the best. But we don't live in that kind of world, right? We live in a world that's populated by a bunch of other people who've already solved a bunch of these problems, and generations before us who've actually sculpted the world in a way that we're not constantly in this worst case kind of situation. And so if we're actually able to learn not just from interacting with the full version of the problem right away, but maybe simpler problems that are getting harder over time because we start off in kindergarten and then we go to first grade or whatever, that you don't necessarily need to do any of this stuff. You end up you need to develop a very different kind of algorithm, but at least it will have the property that it's not going to rub up against everything in the entire world to decide what's good. But it depends very heavily on an environment that is friendly. And I think we have that kind of environment, but we don't really have algorithms that know how to take advantage of it.
First of all, I'd like to thank you for this great talk.
Oh, sure.
So model-free reinforcement learning methods like UCT, they also basically rely on this assumption of optimality, right? So I haven't seen the proofs for, say, E cubed or Rmax, but I'm wondering, basically, do their results, convergence results, convergence speeds, are they proven in the same way? Basically, are there mathematical reasons for why you need the optimality assumption, both in model-free and model-based methods? Are they roughly the same, or the principles are just totally different?
Okay, so let me see if I can repeat the question back and see if it's what you intended. So there's model-free methods and there's model-based methods. The model-free methods kind of explore and try to directly learn a value function without actually ever building transition model. And often they will use some kind of optimism there, like maybe the values are initialized high and then they have to push them down during learning. Then the model-based methods build a model and they inject optimism directly into that model and then plan, and we have some kind of guarantees for those. And like, how do the guarantees in those two different settings relate to each other? Is that the question?
Yeah, basically, do the guarantees hold for the same mathematical reasons?
So we have proofs for the kind of versions of Q-learning, we call delayed Q-learning, that build on the same mathematical machinery, yes, where the idea is that because you have optimism and things are slowly getting pushed down, we just have to be able to bound how long is it going to be before you push it down to something realistic. And both proofs in both cases work with a lot of the same machinery. One of the things that's interesting, though, is that at least in the theoretical sense, the model-free methods shave off a factor of the state space from the bound. So whereas the model-based methods have to learn this sort of S-squared kind of structure, the model-free methods seem to be able to do with just S, like the size of the value function, states times actions, instead of the size of the model, which is state squared times actions. So that's weird, because those algorithms are not as good as the model-based algorithm. You run them and they just take forever, but the bounds are not as good. And I think there are some recent papers that actually show you can shave off the S from some of the model-based methods as well by coming up with very cartoony kinds of models that are good enough for planning, but not really good enough for very accurate prediction.
Thanks.
Sure. Hi, Drew.
Hi. So it seems as if, excuse me, your niece was a little bit smarter than you're giving her credit for. I mean, in all of your models, the system is essentially immortal. That is, even if it dies, you get to run again. Whereas the idea of taking candy from every stranger on the assumption that, you know...
Technically, I was not a stranger. Everyone around her was telling her that I was part of the family. But yes, no, you're right. So the unbridled optimism leads to taking candy from strangers. It's exactly right. Like, I'll try anything because what's the downside? The downside is that I'll lose a little reward now, but I'll learn something, and it'll maybe in the long run it'll be fine. In human life, right? You know, what's the downside? I'm dead and I don't get to learn anymore. Right? So that's a bad downside. So you have to be very bad downside. So you have to be very, very careful about that. So the way that this has been translated in this part of the world, this field, is a couple ways. One is you can put hard constraints, right? You can say some actions you can't take in some states. You know, the rule is you can't take candy from strangers. For family members, you can decide whether it's a good idea, but for strangers, no. And that's really hard to do because somebody has to come up with those constraints in advance. It's good because then you get nice guarantees, but it's bad because it's hard to know how you'd actually specify these rules. Another thing that some people have done is to say, okay, well, let's forget about this optimism thing. Let's actually be pessimistic or maybe realistic, but we're going to depend on an expert to take us through the state space a few times so we get to know which sorts of things are safe. And then everything else that we don't visit, we're just going to assume is a little bit dangerous. And then you can get guarantees that say, well, the learner will do at least as well as the demonstrator did, but not necessarily optimal, because it can't be optimal because it's afraid to try some of the transitions that are out there. And so as long as you have a demonstrator that actually can show you enough of the world that the good stuff is there, you get a pretty good guarantee. All right.
So if I understood correctly, when you do the planning, you're basically using the KWIK model in a sort of like a generative model.
Yes.
Aren't you losing something? I mean, you showed that you're learning basically in some cases where you supply something like a dynamic Bayesian network, you're learning a model that could be used to generate good heuristics.
Right. So could there be a way, let me try to rephrase it and then I'll give a short answer. So could there be a way of actually using the structure that we know that the learner had to use anyway to be able to learn the environment? Can't we maintain some of that and bring it over onto the planning side instead of just throwing it all away and just saying we have a generative model? Probably. Thank you very much.